Thank you. So, just to introduce myself again, I am Charles Fabijanic, and this is my presentation, Supersonic Flow Diagnostics using Optical Nozzles. This work was done also with another PhD student named Ola Al-Habib, and my advisor, Dr. Jordy, who's an associate professor in the Department of Mechanical Engineering. So, there we go. So just to outline the presentation, I'm going to go through some introduction and background to the theory behind this, my experimental setup, results and discussion, conclusions, and some of the future work we're planning on doing over the next year or so. So to give an introduction, supersonic and hypersonic flow has become an increasingly important research area. It's important for space travel, military applications recently on maybe commercial transportation. But right now there are larger gaps in hypersonic research, especially in the U.S. compared to some other countries. So with this, we're trying to design different testing methodologies to create simple testing procedures. We also want to put a focus on visual techniques such as using pressure sensitive paints or particle image velocimetry to accommodate that. Kind of going to the motivation, we want to be able to create cheap and effective ways to be able to conduct this research. So some of the ideas we're working with is we want to make these nozzles fully glass to make them fully accessible for these optical techniques. So we use glass blowing for our nozzles. In our case, it turns out to be relatively inexpensive, and with a skilled glass blower, you can make very accurate nozzles. We need to be able to allow the diagnostics to occur at various regions, inlet, expansion, throat. So that's kind of the idea with doing the full glass nozzles. So the goal of this study is to kind of gauge different techniques, abilities to collect results from our testing. Kind of go into some background. So we're using a converging and diverging nozzle. The physics behind this operates based off, we're trying to choke the flow or reach the maximum flow velocity, or not maximum, reach sonic flow or Mach 1 flow at the throat of the nozzle. So this is done by converging on the nozzle area or reaches an ideal area in which it will be choked and can no longer accelerate past Mach 1. After that, we go ahead and expand it, and this causes the flow to accelerate. You can expand, there's different ways you can do it, isentropic flow relations. In our case, we use method of characteristics, which is a numerical simulation method, or the Rao approximation, which is kind of an analytical equation to figure this out. We're using various non-intrusive flow diagnostic abilities that have been shown to have good ability at seeing a lot of like complex flow structures that occur in supersonic flow, such as pressure sensitive paint, background oriented Schlieren, particle image velocimetry, and shadow graphs. So I'm going to briefly go over kind of the nozzle and wind tunnel design. We had two nozzles made, a Mach 2 and a Mach 5. It should be known though with the Mach 5, because we don't have a vacuum chamber built yet, it's highly unlikely to get fully isentropic expansion, so it's probably not going to be able to operate actually at Mach 5 conditions. So the inlet for both nozzles were designed via the Rao approximation, stating that the radius of curvature should be 1/2 the radius of the throat, so the thinnest portion where we're trying to achieve that sonic flow. And then one of the nozzles, we designed the expansion using the Rao approximation, which is just based off a parabolic formula that you use until you reach your ideal exit area ratio. And the Mach 2 nozzle was designed using, expansion area was designed using method of characteristics. It's a pretty simple setup. It's a high pressure tank on the inlet side. blow down to atmospheric pressure. This is released using a high pressure solenoid valve, and the nozzle is just clamped to the piping that we use via rubberized exhaust clamp. So for PSP, our PSP setup, we conduct this by shining a UV light of a certain light frequency onto a painted surface. When we run a test on the addition of air or reduction of air, will kind of create like an oxygen quenching effect on the paint. This will cause the paint to emit different signals. So in our case, we need a 550 nanometer camera light filter in order to pick up these signal differences that we'd see on our paint. The two models we made were printed out of 3D printing material called VisiJet Armor. This is a pretty tough material to try and print out of. We used two different models as well. One's an 11-degree wedge, and one is a contour of the wall that was designed based off the 3D model schematics of our nozzle expansion. So next, we did some background-oriented schliering. So this is conducted by trying to view any kind of variation discrepancy that would happen on, say, a background image, so a speckled image like we have here. We use a Davis Levision Imager LX2M camera for taking the images and use a speckled texture image generator to create the background images. It should be noted that these images should be fairly high resolution. Each speckle should be approximately 5 pixels in diameter. And we also used a high illumination light source to try and make any of the variations we would see in the air inside the wind tunnel as visible as possible on the speckled imaging. And then we used two different ways to process it. Davis 10, which is a Levision software, in a PIV processing mode. And this would try and correlate any of the pixel shifts that would happen between a wind off and wind on image. We also used a MATLAB program that's available online. Another methodology we did was shadow graphs. So similarly to before, we use a Davis Levision Imager LX2M camera for imaging and a high intensity light behind the nozzle. We just used a plain white sheet of paper to cast a shadow on. And because of high humidity on the day of testing, it caused condensed water to be visualized. So this testing was almost similar to more like a particle shadow loss symmetry, where we're trying to trace the particles, the shadows of the particles through our nozzle setup. Our last testing method was particle image loss symmetry. So in this, we use a double pulse ND-YAG laser, pulsing at a 532 nanometer wavelength. Once again, use a Levision Imager LX2M camera in double frame mode to be able to capture the double pulses that happen in our laser. So far, we've only done tests with hollow spheres for seeding for the particle image loss symmetry. These have a fairly large diameter compared to what you traditionally use, 5 micron ideally. You'd be trying to look for sub 1 micron for high-speed testing, so it's not ideal, but it's still good enough to give us kind of a general feel for what to expect during the tests. All right, so start getting into some results. So first I'll kind of discuss the PSP testing on the wedge. So these are 3 average plots that we have, ranging from 3 atmosphere inlet stagnation pressure to a 5 atmosphere inlet stagnation pressure. So first, with the lowest pressure one on the left, we see a relatively subsonic trend across the surface. but as we increase the pressure in our testing, we will get a very sharp high pressure region on the tip and then low pressure right afterwards. Um, Pressure sensitive paint in this case proved to be pretty viable, pretty easy to see the pressure mapping that should be occurring on the test objects. Next, I'll kind of discuss our contour or insert. So at 3 atmosphere stagnation pressure, you can see in the going from the top left to the bottom right, you can kind of see uh, how uh, how the pressure mapping changes throughout the entirety of the test. So you can see in the in the first two images um, we have kind of a slight supersonic trend right there where we have that lower pressure coming off the inlet section, but it rapidly increases. And then as it reaches steady state during the duration of the test, um, it's relatively uniform. There's no variation. Uh, as we increase the pressure though to 4.42, uh, especially in the second image on the top that we see, the middle image, we can see that we're starting to get much lower pressures coming off of the throat, uh, but still kind of steadies out pretty easily. But the big key here is it's easy to see these variations through the tests, which is uh, shows promising results for being able to do pressure sensitive paint. The final test we did was at 9.19 atmospheres stagnation pressure on the inlet end. Uh, we can see a very clear, like as the test continues, we see a very clear drop in pressure, um, which is kind of what we'd expect. Very low pressure coming off of the throat section. One thing that we did not expect to see though was that very sharp increase of pressure. So that corresponds to kind of the end of the expansion of the nozzle. So that would be kind of indicative of possibly a normal shock occurring there, but we need to look into that further. It could be caused by the insert causing interference inside the nozzle, so we'll have to do some more diagnostics to determine the cause of that. So moving on to some background-oriented Schlieren results. Uh, in the glass nozzles, we were able to in fact see some of the density gradient changes that happen in our testing. So you can see uh, in this first image on the top left, we have a pretty significant a pixel displacement occur out in front of our wedge shape. But what was interesting was that we didn't see anything necessarily form from the wedge itself, but the bolt we used to attach the wedge uh, to our test vehicle fixture. So this is kind of similar to what you'd expect to see with like a needle. So we might have to get a bigger shape, a bigger wedge shape to try and create a stronger shock wave, be able to see it just to verify. In our MATLAB code, we're able to kind of replicate these results where we don't have that displacement happening after uh, after that bolt head. We have a much larger displacement occurring ahead of it, and that was and that was done using a MATLAB code. So we also tested a blunt object. So this one we got a bit more clear results as far as like a pixel displacement occurring. So there's a strong pixel displacement occurring out in front of the blunt object, and you can kind of see it wrapping around the curvature of the blunt object. So this would indicate that there's a strong displacement, strong density gradient occurring just out in front of the test object, and that could be due to a bow shock that would normally occur when testing with a blunt object. but we need to kind of continue to improve our results using the Davis software and improve our technique to get better results with the Davis software, I should say. So we got uh, next, we have some preliminary particle image velocimetry studies. We still need to work on our refinement of our seeding process, but we still were able to get some results so far. On so with this, we only tested with our Mach 2 nozzle. On and once again, we use large diameter hollow spheres, so we're not going to be able to see very fine details that occur. But you can kind of see in the top image, we do have a pretty high, uh, a large velocity that suddenly stops and goes to a subsonic velocity. So we go from a supersonic to a subsonic velocity range, which actually corresponds with uh, our normal shock equations that we have. So uh, furthermore, when we did our shadow graph testing, we could actually see this unsteady kind of shock in our recordings where it's moving kind of out in front of the test object back and forth. This could be, uh, in this case, we think it's a symptom of overexpanding the nozzle. So the pressure was uh, too low in the expansion zone of the nozzle, which induced a normal shock in that portion. Uh, and that makes sense. We were running at a pretty low inlet pressure in the case of these tests. So, so we need to uh, use a higher inlet pressure and keep testing and see if we can continue to replicate these or have this phenomenon go away. I'd like to just kind of conclude some of our early results. So we've been using a Mach 2 and a Mach 5 glass nozzle. The results are fairly qualitative so far, and we need to work more. But now that we've kind of got a feel for how testing is going to go with these glass nozzles, we're going to move to getting more quantitative results. So far, PSP has yielded the easiest results to see, easiest test setup, uh, and really required the least amount of work to get to work. Background oriented Schlieren, we were able to see some density gradients. I think we need to just work with improving our speckle pattern in the background and our placement of that pattern, how well we can focus on it to improve our ability to see these pixel shifts occurring due to that change in density. Particle image velocimetry and the shadow graphs still need to be worked on more, especially the PIV will probably prove to be some of the most exciting results. It'll probably be our most looked at quantitative results that we go for. So just to kind of highlight some future work that you might see coming from our lab. We're planning on doing a lot more particle image velocimetry. We're going to start up a big PIV campaign coming in the next few months. Another thing we plan on doing is conducting tomographic PIV, so that'd be the 3D variant of what you saw. We're going to continue refining our background-oriented Schlieren by improving background image quality and seeing how that works. And then shadow graphs actually have appeared to be some of the more difficult tasks, or is going to be one of the more difficult tasks to improve moving forward. Some of the issue you have is the shadow distortion coming out of the nozzle is quite significant. So we need to find a way to change how the light is refracting through the nozzle to improve that technique. Right, so just some quick acknowledgements that also helped us with our experiment. I'd like to thank Rob Seiler. He's an NDSU ME Department Lab Manager. He's helped a lot with the 3D printing. Will Reffling, who's another PhD student, he helped me do the background oriented Schlieren test, and Dr. Brian Rice with the Air Force Research Labs at Arnold Air Force Base. He helped me kind of develop some of these ideas and has been helping me going forward to how to improve these techniques. All right, thanks.
Okay, if we have any questions for Charles, you can post them in the chat. And we have our first question. Did you account for temperature effects in your PSP measurements? Charles?
Yeah, so we did measure the temperature, so we were kind of using a relative temperature, but one of the nice things about using a binary PSP that we did, that we use is it outputs two signals. One would be like a reference and one would be the pressure signal. So it does a fairly good job at compensating for any temperature effects that would happen. So does that answer your question or?
Yeah, I think that probably gets to what Jeff's question was. How responsive is the paint? Is its response time? How fast is its response time?
I don't actually remember off the top of my head, but yeah, it's not terribly fast.
Like seconds of response time, or it has to get a steady state?
It's not like I think it's in maybe the millisecond range. Yeah, I'm not positive right off the top of my head. I'm pretty sure it's in the millisecond range. We do have fast PSP that we're also going to be looking into from ISSI. That stuff will respond in microsecond range, so that should be a lot better for testing. But yeah, hopefully that answers your question. Well,
We got another question. It's from Alex. Did you notice any advantages or disadvantages for the different speckle patterns for the BOS?
yeah, for the speckled patterns, what I've done so far, by having as refined, like as small as a speckle pattern as you can get, down to about that uh, was a 5 pixel diameter per speckle. That started to yield pretty good results, or better results. Uh, but then you start having some issues with how well you can focus. We're kind of space limited, so trying to find optimal focus ranges became harder, but it seemed to yield better results. The less refined the speckle patterns seem to be, like the larger the speckles, the more it seemed to miss out on. So yeah, so just trying to aim for like, we also notice as random, uh, the more random the speckles were, the better the results seem to come out. We're doing like a very grid-like pattern. Uh, yeah, hope that answers your question.
Thanks, Charles. Any more questions for Charles? Hey, Charles, this is Glenn. Do you have any ideas for follow-up research?
You mean like continued work with this, or?
Sure.
So, right now, one of the projects we also plan on doing after this, I believe, is going to be a seeding study. So we want to look at primarily oil-based seating in these conditions to see how well they respond in cryogenic conditions if we're going to have to deal with the oil actually freezing during the tests. So that's one of the follow-up projects. But yeah, right now it's kind of trying to get the two different nozzles working as they're supposed to. Like get up to the hypersonic one and get it to work well. So hope that answers your question. Also, to get back to the PSP question, I was able to remember it's about 300 milliseconds for the PSP response time. So yeah, hope that answers your question.